Have you ever seen a cheetah just turn into a snail? I mean, that's kind of what can happen to your code, right? So today, we're going to demystify this whole thing. Why applications that start out super fast can suddenly just grind to a halt. And more importantly, how you can stop it from happening. It's really all about thinking ahead. Okay, you know this story. It's super frustrating. You build an app, and on your own machine, it's a total speed demon, blazing fast. But then, it hits the real world with thousands of users. As all that data starts piling in, the performance just takes a nosedive. But here's the good news, and this is important. It's probably not your hardware failing you. It's actually a code problem, and that means it's a solvable problem. So the answer, it lies in this concept called algorithmic complexity. And I know, that sounds kind of scary, but trust me, it's not. All it really is a way to predict how your code is going to perform in the future, especially as the amount of data grows. And honestly, it's the absolute key to building apps that don't just start fast, but actually stay fast. All right, so how do we actually measure this stuff? Well, we have this fantastic tool for the job, and it's called Big O Notation. Seriously, just think of it as a diagnostic tool that lets engineers, like us, look into the future and see how our code is going to behave.
So Big O notation, it's kind of like a weather forecast, but for your code's performance. It's not going to tell you the exact speed in milliseconds, right? But it will predict the trend. Like, hey, if the data doubles, is your app's runtime going to double too? Or is it going to be like 4 times as long? Big O is what gives us those answers.
Okay, let's look at a really simple example. Imagine you're searching for a name in a big list. Now, the absolute best case scenario, what we call O1, is that the name you're looking for is the very first one on the list. Boom, you're done. Instant. But let's be real, that rarely happens. In reality, you'll probably have to go through that list one by one, item by item. And that is what we call ON, where N is just the number of items. So if that list doubles in size, guess what? Your search time on average doubles too. Okay, now this is where it gets really interesting. Let's think about these different complexity levels like they're competitors in a race. We're going to keep adding more and more data, and we'll get to see which of these approaches can actually keep up, and which ones just get left completely in the dust. All right, here are our racers. First, you've got O of 1. This is the Usain Bolt of algorithms. I mean, its speed is totally constant. It does not care how much data you throw at it. Then there's O of log n, which is amazing for searching. It's like a genius librarian who can find any book by just cutting the search area in half, over and over. O of n is steady, but its time goes up right along with the data. O of n log n is what you see in really efficient sorting algorithms. And then, oh boy, then we have O of n squared and O of 2n. These are the ones that start out looking good, but they are going to run out of steam fast. Think of a simple bubble sort that has to compare every single item to every other item. Yeah. Not great. So, you ready to see this race in action? We're about to crank up the data size by 100 times. Let's see how our little algorithms handle the pressure. I think the results are going to surprise you. First up, our O of log n algorithm. Okay, get this. Even with 100 times more data, it only gets 8 times slower. That is incredibly scalable. It barely even breaks a sweat. Okay, next is our O of n algorithm. And just like you'd expect, 100 times more data means, well, it takes 100 times longer. It's a very direct, predictable relationship, but you can already start to feel it dragging a little bit, can't you? And now, the ON square algorithm. This is where the race just gets brutal. With 100 times the data, it's a staggering 10,000 times slower. Wow, this is exactly how an app goes from being lightning fast to being completely frozen. And look, this isn't just some abstract theory. This is a serious reality check for every single developer out there. Okay, so we've seen the theory, we've seen the race. But what does this actually mean for the code we write every day, especially in Delphi? Let's bring this all back home with a really common, really practical example. Yeah, this quote right here really gets to the heart of it. There's just no perfect one-size-fits-all solution in programming. You might have a data structure that's amazing for adding new data, but it's just awful for searching that data later. It's all about trade-offs, and the key is knowing which trade-offs you need to make for your specific situation. A good way to think about it is like your code is a skyscraper. The data structures you pick, that's the foundation. If you build a strong foundation, your app can scale to incredible heights. But if you choose a weak one, well, you're going to start seeing the cracks appear as soon as the pressure really starts to mount.
Let's take Delphi's T-string list. Even a simple component like this has this exact trade-off built right in. So in its default, unsorted mode, if you want to find something, it has to check every single item. That's a slow ON process. But, and this is the cool part, just by setting one little property to sorted, it completely switches gears to a lightning-fast O log n binary search. It's the same component, but the performance is just wildly different.
So why does all this matter so much? Look, if your list has 20 items, you are never, ever going to notice the difference. But what about a list with 200,000 items? Suddenly, the difference between ON and O log n is the difference between an instant result and an application that just looks like it's frozen. This is the kind of choice you have to make every single day as a developer, and understanding Big O is what gives you the power to make the right one.
So here's the takeaway. The next time you're writing code, don't just ask yourself, does it work? Ask yourself, but will it scale? You got to look for those hidden performance traps. Because when you think about complexity from the very beginning, you're not just writing code for today, you're building a solid foundation for the future. Thanks for joining me for this explainer.